scheduled start time. So we'll go ahead and get started. Others are still going to be filtering in, and they'll get added to the room here as they come in. This meeting is being recorded. You probably see a message on your screen. If you click got it, you should get that message to go away. And I will jump in and start by saying my name's Chris Lautenberger. I'm a fire protection engineer and fire scientist based in Northern California. And we're here today to talk about the PyreCast wildfire forecast tool. This particular project has been funded by the California Energy Commission under its EPIC or Electric Program Investment Charge. This is a ratepayer funded effort that is aimed to improve grid resiliency in California, provide safe, reliable, and affordable clean energy, and improve resiliency of the electrical grid. So as you'll see here, as I get into things, there's also some associated benefits beyond this. This particular project kicked off in 2019 and runs through 2024. So we're just about maybe 2/3 of the way through. And the principal investigator and project manager for this project is Spatial Informatics Group and David Saw. And one of the first things that we did when we kicked this project off was to give this consortium a name. And the name we came up with is Pyregence, or Fire Intelligence, which really describes a lot of what we're doing here. We just got kind of tired of calling it the CEC project. Now, there are 4 main working groups for this particular project. And we're only going to talk about one today, but I wanted to kind of give a high-level overview of the other aspects of this project. Working Group 1 is led by Janice Cohn, and Working Group 1 is focused on extreme fire weather, as well as weather station optimization. So where are the blind spots for weather stations in California, and also understanding the different extreme weather types that have led to large lost fires or large fires more generally in California. The second working group is focused on fire behavior and developing improved models for fire spread. So this includes both work in the laboratory as well as computational efforts. It's led by Scott Stevens from UC Berkeley. And I'm leading the short-term or the near-term forecast working group, which we'll talk about here shortly. And then the final working group, Working Group 4, is led by Leroy Westerling from UC Merced. And it's focused on long-term forecasts of fire activity in California, meaning mid-century, 2050 and beyond. So really, there's only 2 parts to this presentation today. They're both fairly large parts. But the first part is an introduction to PyreCast and its usage. And then the second part, I'm going to briefly go into some of the data sources and computational models that are used to run this in the background. And we'll finish up with discussion and question and answers if there's any questions or comments. So starting with part 1, I wanted to first introduce our team. There's a large team that has made all of this possible here. And I'm lucky that I get to show off all of their hard work, but really wanted to just acknowledge the web development team that has done a lot of this really nice work that we're about to see. There's folks that have developed inputs for fuels. There is a utilities analyst that is looking at some of the potential economic benefits of this. We have GIS folks and operational folks as well. So really, it's quite a diverse interdisciplinary problem. And I'm going to kind of do a hybrid here where rather than working off of slides the whole time, I'm going to go to a web browser. And the URL for this tool is pyrecast.org, pyrecast.org. If you enter that into your browser, you'll be met with this disclaimer, which we take very seriously. It talks about how this is an experimental tool. It's in a beta testing phase, and this is to be used at your sole risk. If you go down to the bottom, you can read the terms of use and the privacy policy. Once you click accept, you'll land on this page here, which should be pretty familiar and intuitive if you've used Google Maps or Google Earth, which probably everybody on this meeting has. So in terms of basic navigation, start with the base maps, and let's move to California. Okay, get California centered there. The default or the map that you'll land on is this street topo map. There's of course a satellite, and then the one that I tend to use the most is kind of a hybrid that has a satellite with some of the streets and place marks. So you can toggle back and forth or select different base maps there, just as in other tools similar to this. In terms of assets at risk, so one of the things that this tool is aimed to do is to forecast potential impacts from wildfires to assets at risk. Being a California Energy Commission funded project, one of the things that's of interest is of course the location of transmission lines, not just in California, but beyond. And the reason for that, I think, was illustrated last year during the bootleg fire, where this 500 kV corridor in Oregon was affected by the bootleg fire at a period of time where we were in the middle of a heat wave and was very close to exceeding the electrical demand or the demand was close to exceeding the available supply if those transmission lines were taken out. This is from the HIFLD Homeland Infrastructure Foundation level data set. This is all publicly available information. In fact, everything I'm showing here today is publicly available. There's no proprietary or confidential information in this. Another important asset at risk is, of course, structures. And you can toggle on the location of building footprints by clicking that Structures tab. And this covers not just California, but most of the Western US as well. So those are two of the main assets at risk. Other things you'll see here are related to real-time situational awareness. So we have some things for satellite fire detection, for example. If we toggle on MODIS and VIIRS, what that will do is load in some hotspots that have been detected by orbiting satellites within the last several days. And the coloring scheme here is such that the kind of brighter the colors are, the more recent those detections are, and the cooler those colors are, the farther in the past they were detected or that heat was sensed. So you can see this Left Fork fire burning near Bryce Canyon in Utah, which I'll talk about here shortly, is it's currently the most active fire. There's some other fires that were active as recently as a few days ago. So the Pipeline and Haywire fire here in Arizona was quite active, but there's been a push of monsoonal moisture into New Mexico and Arizona that's really quieted these fires down. So you can toggle on MODIS and VIIRS. Look at the real-time satellite data, GOES 16, which is the satellite positioned over the eastern part of the US, covers the entire continental US, which is why we use that. You can see there's a fair amount of cloud cover. Don't see any smoke coming from these fires at this point, although Left Fork is probably putting out some smoke at this point. The real-time perimeter data is brought in, and you can toggle that on or off by selecting this NIFS perimeter box there. Okay, so that's some of the kind of satellite remote sensing data. One of the useful aspects of this is looking at real-time fire behavior from the Alert Wildfire Camera Network. So you can toggle that on or off by selecting or hitting this Hide Cameras button. And each one of these cameras has a feed associated with it. And so if we were to pick a particular camera, there we go. So we have the Alder Hill camera north of Lake Tahoe here. And let's see, we have 10:39 a.m. Oh, sorry, we have 11:41 a.m. So this is the current view that this camera is seeing. One of the kind of nice features of this system is we can look at the terrain in 3D. So to do that, you can click this mountain. It says enable 3D terrain in the lower right-hand corner. And then this transitions from an overhead view to a 3D view, similar to what you might be used to in Google Earth. And this binocular button zooms the map to the camera angle. So if you were to do that, we have now positioned the viewer in the same, roughly the same orientation that the camera is looking at. So using this as an example, here's Prosser Creek Reservoir in the map. You can see it here. And then off in the distance is Verdi Peak and Cone Peak. So this is particularly useful when there's a active fire that's burning, because you can compare the fire forecast data in the model or in the system to what is occurring in the real world. So you have that kind of real-time situational awareness. I'm going to turn off the camera, go from 3D back to 2D. And another important aspect of this is fire history. So fire history is a good indication, or can be a good indication of where fires are likely to occur in the future. And because of the reduced fuel load, it also, of course, affects fire behavior. So if we were to toggle on fire history by clicking this, this clock button here, we can see, in this case, it's 20 years of fire history. So we have a lot of fire history in this area, including some large fires last year, the Caldor fire, King Fire from 2014, and then, of course, the Dixie Fire. So that's a good way to kind of get a quick overview for a particular area of the relevant fire history. Now, I'll note here, there's a button in the upper right corner that says login. And for general users, there's really no reason to log in and create an account, although you're welcome to. What this is intended for is for organizations or users that have proprietary or confidential GIS data that they'd like to add. So for example, if a utility wanted to include its assets as either just an overlay or potentially as an ignition source, for example, for public safety power shutoff, then authenticated users can use this button. Another thing that will be deployed here within the next few weeks is a match drop feature, where authenticated users can basically ignite fires at particular locations on the landscape to see how they would grow and spread. Okay, so with the kind of basic navigation out of the way, I wanted to move on to these tabs here at the top. You'll note there's 4 tabs. It says fuels, weather, risk, and active fires. I'm going to go through those one by one just to show some of the things that can be done here. So if you click fuels, you'll see that the map changes to a 30-meter grid of fuel type. And if you're familiar with fire behavior modeling, then these numbers or these codes here mean something to you. If you're not, they probably don't mean all that much. But what these are is different surface fuel models, different stylized fuel models that provide fuel loading, fuel bed depth, things like that across the landscape. And those are inputs to fire spread models that take that data and combine it with things like wind and slope and fuel moisture and are able to estimate or calculate fire spread rates. So we're looking currently at the surface fuel model, which describes what's on the basically the surface, of course. There's other things here related to topography and canopy layers, but I wanted to just stay on surface fuel model for the moment. Under source, you'll see a few different options. Land fire 2.2.0, that is the current release from the federal land fire program. It is a 2021 capable product, meaning it has disturbances through and including 2020, but not 2021. California Forest Observatory is one of the partners for the Pyregence consortium. They have developed higher resolution, in fact, about 10 times higher resolution fuel input. And we'll look at some of that here in a minute. And then the 2022 California Fuelscape has been developed by Joe Scott and his team at Pyregence. And I'll just show some of the differences that we're going to see in these different products here, particularly in the recently disturbed areas. So let's go back here to Landfire. And remember, this is a product that includes disturbances, meaning fires, through 2020, but not 2021. And if we turn on our fire history here, we see the Caldor fire, which many of you are familiar with or remember from last year. And I'll toggle that off. And this green color means, if you look at this legend here, timber understory 5, which is a typical timber surface fuel model. And if we were to go to, say, the 2022 California Fuelscape developed by Pyregence, you can see that it includes the effect of the Caldor fire on those surface fuels. Similarly, if we were to go up to the Dixie fire in Landfire, you can see all this green. This is virgin forest. And in the 2022 California Fuelscape, you can see different surface fuel models that account for the fact that that's been recently burned. So in all of the fire behavior work that's done in this system, the default for anything in California is the 2022 California Fuelscape, which is a 2022 capable product. And elsewhere, we're using Landfire 2.2.0 with last year's fires burned in as a timber litter fuel model, which is kind of a typical approach. Not quite as detailed as what Pyregence has done here, but it works reasonably well. All right, so there's other other types of fuel inputs here that are relevant. We can look at some of those. Why don't we go down to Placerville? That seems like a good place to look at some things here. So I'm going to go back to Satellite Street, and why don't I turn the opacity down? That's a good way to do it. Okay, so if you're not familiar with Placerville, it's in the Sierra foothills. It's kind of a classic wildland urban interface area. I'll turn on structures, which might take a minute to cache here. There we go. So lots of structures out in areas that could certainly burn, relatively high risk area. And if we, let's go and look at, say, canopy cover for these different fuel product or these different products here. Turn the opacity back up. So in Landfire, remember this is a 30-meter product. You can see how canopy cover has been mapped. The areas where you can see through to the underlying structures or the underlying satellite imagery are areas where canopy cover is 0. So this is at 30-meter resolution. And we can look at, say, the California Forest Observatory product, which is at 10-meter resolution, about 10 times the resolution of the base products. And you can see there's much more differentiation in canopy cover that appears at this 10-meter resolution than at the 30-meter resolution for the base products. So this is a significant improvement spatially for being able to model wildland urban interface fires. We're currently waiting for an update to a 2022 capable product for from the California Forest Observatory. We understand that should be available here in a couple of weeks. And at that point, we'll be running for fires in California with both the Pyregence California Fuelscape data at 30-meter resolution, which is based on Landfire, as well as the 10-meter California Forest Observatory product. Which will be a real interesting comparison for fires burning, particularly through wildland urban interface areas. Okay, wanted to transition from fuels to weather. So, of course, to be able to model the spread of a fire, whether an active fire or fires that might occur in the future, we need to know not just fuels and topography, but also something about the weather. And I should introduce here that this has a temporal component to it. And so this is the first time-aware layer that we've looked at. You see this time slider down at the bottom, and it has both UTC, or Coordinated Universal Time, as well as local time. So typically we think in local time. So let's change this to local. And over here on the right, you can see forecast start time. I'm just going to go back to UTC for a minute. So the weather models refresh every 6 hours, 4 times a day. And we're looking at the most current, or the most recent forecast, which is today's 12Z forecast, which in local time with 7-hour offset is 5 a.m. local time. So this forecast ran at 5 a.m. The weather models that are used here that form this forecast are currently a hybrid of the HRR, the high resolution rapid refresh model, the NAM, the North American Mesoscale model, and the GFS, or the Global Forecast System. And one of the things that's underway is to expose these models individually, as opposed to all together as a hybrid, as we're doing here, as well as some additional models, including the National Blend of Models, or NBM. But for now, there's a single model, which is this hybrid of these three different operational weather models. And right now, the main story weather-wise for California is the heat. There's not a whole lot of wind out there, fortunately, but it's certainly going to be hot this week. And so let's take a look at that. There's a few ways we can look at things. I like to use the point information tool to look at a particular area of interest, or point of interest. And so I'm going to leave that enabled here. You'll see there's a time slider, as well as a kind of play button. So I'm just going to hit play here. And what you'll see the first time this goes through is usually a little bit of blinking. The reason for that is this is being sent over the wire. Nothing can happen instantaneously. And so there's a little bit of choppiness, at least the first time this goes through. Once that's been cached, if we were to back this up now and let that play, what you'll see is a little bit smoother. All right, so if you want to see how things are changing spatially, that's one way to do it. Often you might be interested in just a particular point in the future, and to get there, it's usually easier to take this time slider and move it back and forth to the particular day or time that you're interested in. So that's what I've done here. So Central Valley, the foothills, pretty much everywhere is going to be relatively hot, of course, the exception of the High Sierra. And why don't we pick an area in the foothills here, heading up the slope, and look at what we have for temperatures. So temperatures approaching 100 degrees today, and that heat is coming concurrently with relatively low humidities, down around 20%. If we were to go to more of the Central Valley, it's going to be even lower, down into the 10–15% kind of range. And what that means is that fuels are starting to dry out. Well, they've already started to dry out, and they will continue to dry out even more. This is a drying force for both the live fuels and the dead fuels. One of the things we can look at here is fine dead fuel moisture. So this is formally the equilibrium moisture content, which is a function of relative humidity and temperature of the fuel, but it's very close to the 1-hour fuel moisture, which is what controls ignition or ignitability of a fuel bed given an ignition source. So when fine dead fuel moisture gets down around 2 or 3%, it's really ignitable. It's hard to drive fine dead fuels any drier than about 2%. We see a couple instances where they're actually hitting 1% here. So what this means is that with the fine fuels drying out in this heat, I would expect that we're going to see some fires in these areas over the next week or so, as we often do in California this time of year during fire season. Some of the other things that we can look at here, wind is of course a big factor for fire spread. And we have a wind gust as well as sustained wind speed. And let's dial up the opacity a little bit. So although it's pretty hot and dry this week, there really isn't all that much wind in the forecast, maybe a few hours here and there, and localized parts of the state where there's a good push of wind. So we're seeing here, maybe 20 miles per hour briefly this afternoon in certain locations, down by Fresno, for example, maybe 15, 20 miles per hour. So we've looked at temperature, humidity, and fuel moisture independently. Now wind, there's ways that those can be combined into a measure of overall fire spread potential. And one of those is the Fosberg Fire Weather Index, which I'm showing here. And what the Fosberg Fire Weather Index does is it combines relative humidity, temperature, and sustained wind speed into a fuel independent measure of potential fire spread. So it doesn't take into account what's on the ground as far as fuels. It's strictly a meteorological quantity. And large fires have occurred, usually at least large wind-driven fires have occurred historically when Fosberg is above about 50 for a period of several hours. And so even in this relatively windy part of the state for the next few days, we can see we don't really have a lot of concern with regard to this Fosberg Fire Weather Index because it's staying relatively low. If we were to look at this during an offshore wind event, during Santa Ana winds, for example, or Diablo winds in Northern California, you'd see Fosberg values approaching 100 or even exceeding 100 for many hours continuously. Another way to quantify the potential fire weather is using the Hot Dry Windy Index, or HDW. And hot, dry, windy is similar to Fosberg, except it uses vapor pressure deficit instead of relative humidity and temperature. It's a little bit more sensitive to dryness than Fosberg is for that reason. So it's another way of looking at where does the combination of heat, low humidity, and wind contribute to potential for rapid spread. It's also a fuel independent quantity. So these are some of the things that are available for the weather forecast. Remember, this is updating every 6 hours. We're fortunate this year that we haven't had any smoke yet, at least significant amounts of smoke. Right now, the main source of smoke, I'm just gonna get this out of the way here. So here I should just back up and say what we're looking at is smoke near ground level. I think it's about 20 feet above ground level. And the main area where there's some smoke coming from a fire is in Utah by this left fork fire near Bryce Canyon. And so I think that's probably a good segue to move and talk about the next tab here, which is active fires. So let's go to active fires. And right now, there's a handful of fires in the system. The 2 fires that are in California, the Edgewood fire, you may have heard about this one yesterday. This is quiet. I think its containment is at formally technically, might be a better way to describe it, at 20%, but its effective containment is much closer to 100%. And there's a fire burning by the border that's also basically contained. So really the main active fire now in the US is this left fork fire. And so let's take a look here. So this is burning very close to Bryce Canyon National Park. If you've been there, you've probably driven down this road to Rainbow Point, which is the lookout at the end there. And so we can kind of look at what's going on here. And we'll start by looking at the perimeter. So this is the current perimeter, at least the last time this perimeter was updated for the left fork fire. And we can look at the satellite hotspot data, which is pretty well correlated with that perimeter. You can see a few detections outside of that perimeter. That could be either because these areas have burned since this perimeter was last updated, but also because the geolocation error on this satellite data is comparable to the pixel size, which for VIIRS is about 375 meters, and for MODIS, it's about 1 kilometer. In terms of kind of real-time satellite data, we're not going to be able to see much there because of all this cloud cover. if you were to look at this yesterday, you would, at about this time of day, you'd see a lot of smoke coming off of this fire as it's burning. Cameras, let's see if there's any cameras in the vicinity. There's not. So there's no cameras in view here. We see that a lot in these kind of more remote parts of the country, whereas in California, if there's a fire burning, often it's within view of a camera. We just don't have any fires in range of cameras, or at least any active fires in range of cameras at this point. Okay, so I'm just going to turn off some of these layers now. What you'll see here is you can select the fire that you'd like to see a forecast for from this drop-down box, or simply click on the marker and then click to view forecast. Okay, and then what you'll see once you do that is a bunch of different colors that may not be intuitive, and so let me just explain here what they are. If you look at this legend here in the upper left, and I'll kind of line this up so you can see, this blue color is areas that have already burned. So it says burned before start of forecast, meaning these areas have burned and are cold. The areas that are purple here are burning at the start of the forecast. So the fire only spreads from these purple areas. It doesn't spread from these blue areas because the algorithm that has taken all of this hotspot data and perimeter data has determined that these areas are cold. Sometimes that's not the case. You can often, particularly in high winds, have spread from areas that the model thinks are cold. But in this case, what we have is some purple areas here, and maybe if I just switch to the topo, you can see those a little more clearly. So these purple areas here are the areas that the model has determined are actively burning at the start of the forecast, which is 1:39 a.m. Pacific time today. Why 1:39 a.m.? Well, that's the last time that a satellite was overhead and sensed heat on this particular fire. So the forecast start times are dictated by when heat is sensed on a particular fire. They don't necessarily start at 8 a.m. or 12 p.m. or some nice round starting time. It's whenever these orbiting satellites happen to be overhead. Right, so I can go back to satellite street. Gives an idea of what we have there for fuels. We can also look at the fuels tab, for example, to see, oh, it looks like we have canopy cover. Let me go back. And while that's loading, let me turn on fire history. So if we look at fire history, we can see there's been a little bit of fire history in this area, but not a ton. And let's go back to, there we go, back to active fires, turn off the fire history. Now, just like the weather that we looked at previously, there's this time slider and the play animation. And so we can do that. And what you'll see, if you're patient, is fire spreading off of these purple areas. Remember, those are the areas that are hot. The colors here have to do with how long before the current time shown in the slider these areas burned. So bright red means burned 1 hour before the slider time. This kind of mix between orange and red is 2 hours before, and then you can see this gray is five plus hours. So it's just meant to show kind of temporally how this is burning. Now, what's happening here? Well, you see this blue area, and I'm gonna back this up and let it play because it'll play more smoothly now. Okay. Turning on Modus and Veers again, what you can see is that there was some hot spots detected here, and so the algorithm thinks this area has already burned. That could very well be a spot fire. It could also just be this geolocation error on the satellites that I mentioned as well. But what you'll see is when the fire runs into that, it's going to work its way around it because those areas have been determined to be black, to basically have already burned in the model once the fire spread gets there. So that we'll just let that play here for a moment. the forecasts are currently 5 days, so they project spread 5 days into the future, 120 hours, and they're updated nominally 4, maybe 5 times a day, depending on when the satellites are overhead. So you'll, if you come back to this later today or tomorrow, you'll have another forecast start time other than 1:39 a.m. today. I'm just going to pause it here, and I'm going to drag this all the way out to the end of the forecast period, and then I'm going to zoom out a little bit. And so this area that's gray that's shown here is the forecasted spread of this particular fire 5 days from the start time. If we wanted to look at just the kind of that area as a polygon, you can click this isochrones, which means constant time. It's basically the fire position at a constant time, which in this case is 5 days in the future. And that is the area that's forecast to burn in this particular spread model. Now there's a couple of things going on here. You see predicted fire size, median 50th percentile. What's that about? Well, just as weather models run as ensembles to address uncertainty, these fire forecasts also run as ensembles. So we are running not just a single fire spread model, but hundreds. And what varies across each of those ensemble members, each of those hundreds of ensemble members, is the inputs. So we have a baseline set of inputs, which include fuel moistures, wind speed and direction, et cetera. And there's uncertainty associated with those. We don't know that 4 days from now, the wind speed is going to be exactly 22.3 miles per hour. It could be 15 miles per hour, or it could be 30. And so in these ensembles, those inputs are perturbed from their baseline values to address that uncertainty or to account for that uncertainty. And so if we were to go to, say, the smallest, which is the 10th percentile projected spread, have a little bit smaller polygon, and I guess I'll turn up the opacity here to show that a little more clearly. And I'm going to turn off the Modus and Veers here. I don't know why those aren't turning off. I guess I'll leave them on. Okay, so that's the 10th percentile projected spread, which means that 90% of the ensemble members had a larger fire area at the end of the 5-day forecast than this particular one. It's often we find that the smallest, the 10th or 30th percentile spread end up being a pretty good fit to what actually happens. And the reason for that is that these fires are being actively suppressed. There's suppression crews out there, cutting fire line, dropping retardant, et cetera. And in the fire spread models, none of that is accounted for. So all current fire spread models do not account for suppression in really any effective way. That's one of the aspects of the model that's being developed or improved as part of the CEC EPIC project, is attempting to account for suppression, but it's a very challenging problem. So if we were to go out to, again, say this 50th percentile, you see it's a little bit larger fire area. And then if we were to go to the 90th percentile, it's going to be an even larger fire area. And so what are these percentiles useful for? Well, if your previous forecast, say the forecast from yesterday, underpredicts fire spread, so the actual observed fire spread is larger than what the model said it was going to be, then in today's forecast, you might get a better result using a higher percentile, a higher spread percentile or predicted fire size. And then the converse is true as well. If we're over predicting, which could be because of this suppression aspect that I mentioned, then using something like the 10th percentile spread could give a better result. So that's what this predicted fire size and spread percentiles is. You'll notice here under the model box, Elm fire and grid fire. So Elm fire is Eulerian level set model of fire spread. Eulerian is a fancy word for gridded. Level set method or level set model is a way of tracking curved surfaces on a grid. This is an operational fire spread model that I've been developing for about 10 years at this point. And then there's a second model called GridFire. And GridFire is also a 2D operational fire spread model. It's been developed at Spatial Informatics Group by Gary Johnson and Kenny Chung. And the reason that we're using or providing forecasts for different models is that all models make different approximations and assumptions. And so we can toggle from the ElmFire forecast to the GridFire forecast, and you'll see it's significantly larger. And the reason for that is that the ElmFire model is using what's called a burn period to account for the observation that fires tend to be overpredicted in the nighttime hours by models. This is something that all the operational models used, for example, by the Forest Service do. So in the evening hours, the spread rate is ramped down, and then it picks back up in the morning, and that's called a burn period. So a typical burn period could be maybe 6 hours in early season, kind of moderate levels of dryness, and it could be as many as 12 or 14 hours later in the season under a lot of dryness or under high levels of dryness. So Elm, just kind of toggling back and forth. So there's the ElmFire forecast, and then here is the GridFire forecast, which is larger because GridFire is not currently using a burn period to reduce that spread rate in the overnight hours. The point here is that the system or this framework is not tied to any particular model. And in this case, we have two models. We're in the process of incorporating a third model, which is very different from these operational fire spread models. So these two-dimensional models, such as ElmFire and GridFire, they run very quickly, and they work well for wind-driven fires. They don't work well for fuel-driven fires or for plume-dominated fires. And the reason for that is they don't interact with the atmosphere. So in ElmFire, GridFire, WIFDIS, any of the tools used by CAL FIRE or the Forest Service, those are usually uncoupled, meaning fire is not coupled to the atmosphere, and they don't have the ability to create their own wind, essentially. Whereas in certain instances, so under low wind conditions or high atmospheric instability, one of the main ways that fires can spread is by creating their own wind. And that necessitates not just modeling a two-dimensional surface that represents the Earth, but also the three-dimensional atmosphere above it. And so these coupled models like CAWFE, C-A-W-F-E, developed by Janice Cohn, are orders of magnitude, hundreds to thousands of times more computationally expensive than the uncoupled models. So they take longer to run. They can't provide a 5-day forecast in a matter of microseconds as these other models can, but they have utility, particularly for instances where the fire is expected to be plume dominated. The uncoupled or the two-dimensional models are typically going to underpredict fire spread for those plume dominated fires. So we're in the process of adding a third model, in particular Janice Cohn's CAWFE model, which will be used for plume dominated fires where we expect the uncoupled models to not provide a good prediction because they don't include the necessary physics, that fire atmosphere coupling. Okay, one other thing I just wanted to mention here really quickly, but I've got to get this Zoom window out of the way first. You have this arrow here, share current map. So if you're to, here, let me zoom in a little bit. If you're to click that, you can click copy URL. And if I were to go to a new browser window here and paste that in, it'll basically load what we were just looking at. So there's that same view, that particular fire and that particular area of interest. So this is a way, if rather than saying, sending somebody an email and saying, hey, go to this location and click active fires and do this, you can just copy and paste that link into an email or a text message or whatever. One of the things I should have mentioned, speaking of text messages, is although we're looking at this here in a web browser, in Windows on a computer, this is all mobile aware and mobile friendly, so it also works on mobile devices as well. Okay, I think the next order of business is to move from active fires to risk. That's this tab here, and the risk tool is applied only to California, at least at this point in time. And so let me explain what we're looking at and why we're doing this and what we're doing. Okay, so once you select the risk tab, you'll see under ignition pattern 2 different options. It says human caused ignitions and transmission lines. It's actually human and lightning caused ignition, so basically all fires, and then transmission lines. I'll show those independently. But I want to, rather than using relative burn probability, I want to start with fire area. Okay, so each day, twice a day, we pull in a weather forecast and ignite hundreds of millions of fires across California. Their spread is then modeled for 6 hours, and this is done out to 5 days in the future. And for each of those ignition locations, the fire area is recorded, the number of impacted structures is recorded, and maps like this are developed. And so what this is showing is, I'm gonna back up. Why don't I go to sometime tomorrow? Tomorrow afternoon. That's tomorrow morning. Okay, so this is modeled fire area for 3 p.m. tomorrow. And I'll get the query tool and query a particular location. And what you see is this time series showing how the 6-hour fire size varies across the state as a function of time. So just as with the active fires, these fires are modeled as suppressed. In almost all cases, with some exceptions, the actual fires would be suppressed. Okay, but this gives you an idea of the relative fire size over the next 5 days for this particular location. So it looks like today probably has the largest fire size, 6-hour fire size of about 4,000 acres for this particular location. Whereas on Friday, at that same location, we're peaking out at about 1,000 acres. You can see the imprint of some of the recent disturbances on this modeled fire size. So if we look at the North Complex, which was the kind of the merger of the Bear and Claremont fire, that burned with a really high intensity. And so the fuels there, even though this fire happened in, around Labor Day of 2020, the fuels there are still coming back. So you can see a much lower fire area for that particular location. Same for the areas of the Caldor fire that burned with a lot of intensity. You can see that the modeled fire area there is much smaller than in the surrounding areas. Okay, so that's fire area. And another thing that might be of interest is for a fire starting at a particular location, how many structures are impacted. This is much more discrete or localized in nature, because whereas we are igniting fires across the landscape in a pattern proportional to past fire occurrence, not all those locations have structures. The reason why there's limited structure impacts out here isn't because there isn't the potential for fire spread, but it's because there's limited structures in that area. So if we go back to Placerville, this was an area, remember, we looked at the beginning here as a wildland urban interface area. And we can turn on the structures. You can see that fires starting in this area here have the potential to impact a lot of structures, because there's the combination of fire behavior and also structures. Okay. One of the other outputs is relative burn probability. And so what this is doing is aggregating for these these millions or hundreds of millions of simulations, the areas in all of those modeled fires that are most likely to burn for a fire starting at a particular point in the future. So this is tomorrow, or sorry, 2 days from now at 2 p.m. So this accounts for fuels, weather, topography, fuel dryness, past fire occurrence. And what it does is shows potential hotspots on the landscape as far as their potential to burn within 6 hours of this start time here. Now, we can look at, I showed this previously, but we can look at some of the kind of 3D, kind of the topographical features here that are controlling some of this. So you can see in some of the lower areas or the flatter areas, there's lower burn probability compared to some of the steeper areas, and that's due to that effect of slope and topography on fire spread. Okay, that's one ignition pattern. The second ignition pattern is transmission lines. And why transmission lines? Well, let me zoom out. Yeah, let's first turn on the transmission line layer, zoom out, and then pick fire area. Okay, so due to computational resources, we're not modeling fires under transmission lines across the entire Western US, but actually a pretty good chunk of it, including Nevada, Oregon, parts of Arizona, and even parts of Utah. And what we're looking at here is similar to the fire area, or the modeled fire area that we saw for the human and lightning caused fires, but this is now limiting the ignition pattern to directly underneath transmission lines. This is not distribution lines, so there's no distribution in here. And this is all from the publicly available HIFLD data set that I mentioned previously. So let's go to an area where we might get some higher fire activity over the next few days. We're actually in a kind of a relatively quiet period because, as I mentioned before, there's not a whole lot of wind, even though it is hot and dry. And so what this is doing is showing for this particular location, the modeled fire size as a function of time for the next 5 days for a fire starting at this particular location that I've queried. If we're to come back under a higher wind condition, or when there's an offshore wind event, you'd see much higher fire sizes. Similarly, we can look at the number of impacted structures and look at areas where there's potential to impact structures. And here's an area that appears to be particularly high. So this is showing that for this particular segment, and this is broken into roughly 500-meter segments, there's potential to impact structures. That appears to make sense because if we toggle on the structure layer, we can see there's structures in the vicinity of this conductor. And then if we go to relative burn probability, that's showing how the fires forecast or modeled to spread off of those lines into adjacent areas. So what this is doing is showing, using publicly available utility infrastructure data, the potential to model consequence from power line caused fires. And utilities and regulators can use this to look at potential impacts from power lines to assets at risk and plan for things like public safety power shutoff. So utilities have access to their system, their proprietary and confidential data once they're logged in here. Everything we're looking at here being publicly available is just using kind of general publicly available data. Okay, so that is the that's the kind of second ignition pattern here associated back to power line ignitions. Now, we've been looking here in this web map this entire time, and I'll just turn off some of these layers. And that's one way to access this data. But if you were to go down to the lower left here, learn more about this data, you'll be brought to this page. And it says data can be accessed from the following links. There's really three main ways. Interactive data exploration, that's what we've been doing. Fire forecasting data is a web server, and then geospatial data through an API. And so I'm going to actually start with this one and show what you'll get if you go to data.pyregence.org. This is where all the data lives. If you've used web map services before, you'll be already familiar with this. If you haven't, I'll just kind of walk through how it works. There's different capabilities, meaning different ways that data can be served up. WCS is Web Coverage Service. That is raster or gridded data in basically native form. So you'd get for each pixel of value. And that's a little bit different than WMS, which is Web Map Service. That is pretty pictures. That's data that's been styled and is brought in as image tiles. WFS is Web Feature Service, which is vector data. So rather than stuff on a grid, it's data that are lines and polygons and things like that. So this provides ways to bring data into a local ecosystem or a local application using web services. So if we were to click on this WMS 1.3.0 and say copy link address, that's now on the clipboard. And then you can bring this into your choice of GIS platform, whether it's Esri or QGIS or something else. I'll show how to do this in QGIS. So switched from the browser back to QGIS, which is Quantum GIS. This is an open source GIS platform that's really increasing in popularity lately. And we can pull in all the data that we were looking at in the web map into QGIS or into an Esri product or whatever your choice of GIS is. And so one of the ways to do that is you go add WMS or web map service. WMTS is web map time series. Okay, and I'm going to say new, create a new WMS connection, and I'm just going to call it demo. The name doesn't matter. Here's the URL that I just copied onto the clipboard. If I click OK, it's going to sit here and think for a minute. Oh, actually, I have to click connect first. So once I click connect, it's going to now connect to that web map service. It's saying, hey, GeoServer, what information do you have that I can pull in? And it responds with this huge list of data, which is probably a lot more than we can work with. So since we looked at the left fork fire, why don't we pull in one of those forecasts? So if we type left into the search box, that will call this list down to something a little bit more manageable. And why don't we go down to a 50th percentile run, so kind of median fire size projection. And let's see, today's the 22nd, so why don't we go out a few days, go out to say the 20, we'll go out to the 25th, so Saturday, and we'll go Saturday afternoon, which would be, say, 23Z. Okay, so this says fire spread forecast, Utah left fork. This is the initialization time in UTC. The model's elm fire. The fuels are from land fire. It's 50th percentile for spread. Okay, so once I do that, I can click add here and then close. And it's going to sit here and think. And what it's doing now is it's pulling this over the wire from the internet. And there is the same type of stuff that we were looking at in the web map, except now it's in QGIS. Okay, so at that point, you can work with this data just like it's on your local machine. So here we are bringing in a base layer, some Esri imagery. We could bring in the street layer, for example. Okay, so that's how that works. And I'll do one more example just for, I don't know, maybe a weather forecast component. So say we wanted to be able to overlay this on the modeled wind speed from a forecast. Well, we could go layer, add WMS, and wind speed is WS. And that's probably not the best one. Let's do something a little bit closer in. Maybe the 24th. And here we are. So this would be from today's 0Z, actually, let's pick today's 12Z forecast. And this will be 2 days from now at 21 UTC. Add, close. It sits here, it thinks it's pulling information over the wire. And there is the modeled wind speed from this hybrid forecast that we were looking at before. So that's one way to pull in data to your local ecosystem or local infrastructure. Another way, going back to the web here, is to get at the raw data files. So if you go, we were just looking at geospatial data available through our GeoServer. If you go fire forecasting data, that will call up a web server, or point you to a web server. And if we were to look at, why don't we do weather since we were just on weather, go to fire weather forecast. This is the forecast cycle. So we're now into the 18Z forecast, which launched at 11 a.m. local time, in California at least. But if we go back to the 12Z forecast, we could pull in, why don't we pull in a Fosberg fire weather layer for tomorrow. So FFWI is Fosberg fire weather index. This is the date, and then this is the time in UTC. So 23 UTC is 16 or 4 p.m. local time. So if I were to click on that, that'll sit there and download. It might take a minute. I think we're probably getting some load on the server here, and that should land on my desktop, if I remember where that lands. Let's see if it did. Okay, so it landed on the desktop. So now I could go back into QGIS, add that data. Okay, and there's the Fosberg fire weather index. It comes in this weird grayscale because it doesn't have any styling applied to it. If we were to apply a style, it'll look a little more, yeah, there we go. Okay, so that's the ways that are available to bring data in. We have several users that are scraping data, which is not a problem from our perspective, as long as it doesn't impact the server usage. So all this data is out there. It's available by API. It's available by by web server in the native format that is displayed in the web map as well. Okay, so I think that that was about an hour right there, and I probably have a few more minutes here. I just wanted to transition from kind of the high-level usage and overview of this tool to some of the data sources and the things that are used here. I hinted at some of them, I mentioned some of them, but didn't really have a chance to go into any great detail. So at least for the active fires part, this is kind of a schematic of how it's been put together. There's this weather forecast data. There's real-time fire location or remote sensing data that tells us where the hot spots are. There's static or at least seasonally static data like fuels topography. And then all that goes into different spread models, Elm Fire, Grid Fire, Coffee, et cetera, and pushes out fire spread forecasts that are then disseminated to user groups. This happens automatically. So this is a little bit different than the way fire modeling has historically been approached, which is usually there's a lot of manual steps that have to be done. This is certainly not intended to be a replacement for any of the current practices for fire behavior modeling. It's meant to complement that, provide a really quick way, or provide forecast data in a timely way based on the available data at that time. So that's just a little bit different than the way things are done in WFDIS, the Wildland Fire Decision Support System, for example. So in terms of fuel and topography inputs, I mentioned the Pyregence California 2022 California Fuelscape. That's the default in California. Outside California, Landfire, the 2020 update, or Landfire 2.2.0 is used. Those are both 30-meter projects or products. And shortly we'll be using, within California, in addition to the Pyregence 2022 Fuelscape, the California Forest Observatory data at 10 meters. We're also working with the Center for Ecosystem Climate Solutions. They're also working on a fuel product, and we're looking at incorporating that as well. This is just showing the differences between canopy cover and land fire, and in California Forest Observatory, as I showed around Placerville previously. The weather inputs currently are the HRRR, the NAM, the GFS. We also are using RTMA, or real-time mesoscale analysis, for calculating live fuel moistures. The resolution on the HRRR and the NAM are both 3 kilometers. Temporally, it's 1 hour, and it's out to 2 days for the HRRR, out to 2.5 days for the NAM. And there's 4 cycles per day for each of these. There's actually 24 cycles per day for the HRRR, but 20 of them only go out to 18 hours. GFS is a 1/4 degree, which is, or sorry, 1/8 of a degree, which is about 13 kilometers. The temporal resolution there is initially 1 hour out to 5 days, or 120 hours, and 3 hours after that. The lead time there is 16 days. It's also updated 4 times a day. RTMA is hourly at 2.5 kilometer, and this is what's used to calculate the live fuel moisture. So the native quantities that come in from the weather models are things like relative humidity and temperature. Sometimes it's water vapor mixing ratio instead of relative humidity, but if you know one, you know the other. Of course, precipitation, solar fluxes, incoming and outgoing, wind speed, wind direction, all of those things that are needed to model fire spread. And from that, the derived quantities are things like the Fosberg Fire Weather Index, the Hot, Dry, Windy Index, dead fuel moisture by size class, also National Fire Danger Rating System indices. And so this is just showing from sometime last week, I guess the 12th, the snapshot in time for wind gust, and then this is the fine dead fuel moisture. For near real in-time fire inputs, the way that we find out about fires is from some feeds that are updated in real time. So in California, that's the CAL FIRE incidence feed. And nationally, it's the NIFC large fires feed. So CAL FIRE incidence is updated several times per day, typically, at least if there's fire activity. And then the NIFC large fires feed is updated daily. So for fires outside of California, they may not get added to the system for a day or two. Often they might be several hundred acres in size by that point in time. Typically, we're picking up fires in California within a few hours of ignition. We can, of course, also add fires manually if there's some fire that has a high potential for spread or to impact assets at risk, that can be added manually. The hotspot data comes from 4 different satellites using 2 different sensors at 2 different resolutions. The Terra and Aqua satellites are 1 kilometer resolution using the MODIS sensor. Nominally 12 hours, twice a day, each satellite is overhead. And the Suomi NPP and NOAA 20 satellites have a VIIRS sensor on them. And that's higher spatial resolution, 375 meters, also a approximately 12-hour revisit time. And then the perimeter data is brought in, again, using publicly available information. This is polygon data, so it's probably accurate to maybe 30 meters, something like that. Temporally, this is updated maybe every day if we're lucky, often every other day, sometimes every 3 or 4 days. And so all of this works together to basically determine where we have fires and where those fires are actively burning. Remember back looking at the active fires forecast, the blue areas are cold or already burned, the purple areas are burning. And so this is just showing kind of qualitatively how the fire perimeter data and hotspot data are combined to initialize a fire forecast using this near real-time data. I mentioned, or we looked at some of the real-time situational awareness. Just wasn't a whole lot of fire activity. And for last year, there was many instances, unfortunately, where there were very large fires in view of cameras. So this is an example of one of those instances. This was, looks like July 22nd. This is looking toward the Dixie fire. This is looking from the north toward the south toward the Dixie fire. And then this was a new ignition called the Fly fire. So these eventually burned together and merged. But this is just an example from last season. And we looked at the real-time satellite imagery, saw there wasn't really much going on. There's a lot of cloud cover, which is a nice thing to see, actually, compared to this situation, which was about the same time last year. I think this was after the Fly fire had ignited, because we have Dixie and Fly here, but this is all smoke. So these are some of the things that are available. I mentioned that in some instances, you'll have a fire burning where you can also see the topography from a camera. This is an example from last season where we had modeled fire spread in the system, and the camera was moved to the vantage point in the 3D terrain was moved to match the camera vantage point here. So you can see, I think this is Shasta Lake here. It shows as blue in the imagery, but because it was so dry last year, it's actually dry in the actual camera view. So these are some tools or some ways to kind of keep an eye on the fire spread model. Is what the model forecasting will happen, what the cameras are showing, or is there some divergence between those? In terms of computational models, I mentioned we're using ensemble forecasts, which just means rather than running a single fire, we're running hundreds of variations of the same basic fire and perturbing the inputs to account for uncertainty in the inputs. And then those are aggregated into these spread percentiles, 50th percentile, 90th percentile, and so on. And so this image here, or this movie here, is just showing a 24-hour fire spread forecast condensed to 2 seconds. So, and just running that on a loop. And the models, I mentioned Elm Fire, Eulerian level set model for fire spread. The original journal article was back in 2013. It lives in GitHub. It's in a private repository for now. We're in the process of slowly releasing a lot of this code. Everything that we showed today will eventually be released as open source as part of the CEC project. And some of that will happen as soon as next week. Other parts won't be released until closer to the end of the project in 2023 or 2024. GridFire is another fire spread model that's being used. It's also in GitHub. It's a little bit different. It's different programming language. It's what's called a literate program, which is a really nice way to reduce the burden on the end user to get up to speed using that program. So Gary Johnson has done a great job at really making GridFire accessible. It's written in Clojure. Elmfire is written in Fortran, which my father learned when he was in college, but Fortran is still widely used in computational computing because it's can be quite fast. Underlying all these models is the raw thermal surface spread model developed in the 1960s and 1970s. It's the workhorse for all of the 2D operational fire spread models in the US, including Elmfire and GridFire. Dead fuel moisture is calculated from the weather stream using NFDRS, basically the same equations that's used in the National Fire Danger Rating System, by accounting for or using the equilibrium moisture content relative to the current moisture content, and that's calculated for different size classes of fuels, basically different diameter fuels. Live fuel moisture, I mentioned, comes from the NFDRS 2016 using RTMA. We used to also use data from the National Fuel Moisture Database, but that seems like that has gone away this year. And so we're currently using the modeled as opposed to measured data from the National Fuel Moisture Database. Crown fire in both elm fire and bridge fire uses the Van Wagner crown fire initiation criterion, and then spread rate from crews, because we found that it gives a little bit better agreement with observed fire spread rates than the raw thermal 1991 model, which is also widely used. Spotting is modeled and it's treated stochastically. This is showing a probability density function for spotting distance as a function of fire line intensity and wind speed for a few different parameters. So both elm fire and grid fire are doing this. And so that just about concludes what I wanted to cover today. Looks like we do have some time for questions or discussion if there's any questions. And so I will just pause there. It looks like there's been a lot of stuff going on in the chat, but I haven't been monitoring that. So I don't know, Shane, do you want to take over and be the moderator here?
Sure, I can help out. And Gary, you're welcome to join me as well. It looks like Gary's been actively engaging with the chat box, but maybe we can go ahead and just reiterate some of the questions. Or otherwise, if there's somebody that has a question that they want to unmute themselves and jump on and just ask, we can do that as well. But I'll just kick it off with some of the questions that came in. It looks like Gary's kind of responded to these, and you might have a slight variation on the response. But one of the questions came up, can cloud or smoke cover block satellite hotspot detection? If so, does that limit forecasting ability, especially if hotspot detection is blocked on only part of the fire? Chris, you want to respond to that, or? You're muted.
I could not figure out how to get myself off of mute despite having done hundreds of Zoom meetings over the last 2 years. Yeah, that's a really good point. Yes, cloud cover can block satellites. This isn't really my area of expertise, but there's something that we've seen several that's actually probably more of a limitation, and that is false detections outside of the fire perimeter where the satellites appear to be sensing smoke. So there was an example in 2020 during that lightning bust in August, where the satellites were picking up heat over large portions of Vacaville, including really urban areas or really built up urbanized areas. So if you had looked at the satellite data alone, you would think that Vacaville had been basically burned to the ground. But what it was the satellites, because there was just so much heat coming off of off of the fires, they were picking up that heat in the plume and thinking it was active fire on the ground. But yeah, that's a limitation of the satellites. And should mention that the MODIS sensor is quite old at this point. I believe it's being decommissioned shortly. And it's our understanding, again, this isn't my area of expertise, but we understand that there's higher resolution, both spatially and temporally, stuff that's going to be available in the near term, within the next couple of years. And so we're currently using what's available, but would be happy to update that when newer and more higher resolution or improved products become available.
Great, thanks. Another question just came in. Basically, it said that Chris has briefly addressed how fast fires are added to the model. As an example, Onewood yesterday's 20-acre Edgewood fire started around 2:30 p.m. in San Mateo County have been available, I guess, in the tool.
Yeah, that's a good question. So I can go through some of the timing there. So I mentioned we're using these publicly available feeds from CAL FIRE and from NIFC, National Interagency Fire Center. And we can also add fires manually. So we don't have a fire in the system, of course, until it hits one of those lists or until somebody says, hey, there's got wind of this new fire, then we should probably add it because it looks like, it has potential for spread. So once a fire is added to the system, the algorithm will process that ignition and make a forecast, often within a few minutes. So 5-10 minutes would be kind of typical. And then that is available in the web application the next time the scripts run that look for new fires. So our goal is to get that down by using what we call event-based registration. So as soon as a new fire runs, we send a message to the geo server that says, hey, we've got a new fire, it's here, pick it up and add it. So currently it's somewhere between minutes to an hour. I'd say by the by the next few weeks here, we should have that down to a few minutes. So the goal would be to have a fire, once it hits CAL FIRE incidents, have it available in PyreCast within 5 or 10 minutes.
Great, thanks. And then I think you've kind of covered some of this, but Joseph Merrill asked, does PyreCast have an API to add layers via URL links? I don't, maybe you didn't go through that one directly, but I guess you can go through our geo server through just searching for a data layer that you're of interest and then connect that link. But I don't know if you wanted to respond to that or maybe show more specifically how to get at that.
Yeah, so currently we don't have the ability for users to add their own data. So at least in an automated, quick kind of way. So what I mean by that is there are certain web applications out there, and I think Joseph's pointed us to a few of those, where you can add your own geospatial data, bring in, assets at risk or whatever you're interested in, and we don't have the kind of the back end built out to provide that functionality yet. It's on the list, but it's actually a relatively heavy lift to do that in kind of a generalized way. So for now, the way that assets are added is kind of on a case-by-case basis or manually. So if a utility, for example, wants to add their electrical lines, that has to occur on a virtual machine that is firewalled off from everything else using a VPN for security reasons. And so we're kind of focused on the proprietary and confidential information, but don't have currently at least the ability to add for an authenticated user their specific data. But I think it would be a really nice feature to have.
One question came in, what is the underlying fire behavior model? I think you kind of covered that. Maybe you want to comment additionally on that?
Yeah, the main workhorses here are uncoupled to the atmosphere, two-dimensional operational fire spread models similar to things that are used in WFDIS, the Wildland Fire Decision Support System, Farsight, FlamMap, near-term fire behavior, just a little bit different in terms of how it's implemented. So it's all raw thermal based modeling, elliptical dimensions, or from Richards, all of the kind of classic assumptions and approximations that are baked into a tool like Farsight.
And a question came in, how does the change in nighttime vapor pressure deficit, where it has become more acute at nighttime fire behavior and leading to faster spread and higher rates than historical vapor pressure deficit reading, get factored into your modeling?
That's certainly something we've noticed. Like last year, looking at Caldor and Dixie, they often burned actively through the night, and that my understanding, at least, is that wasn't common 10 or 15 or 20 years ago. So we're currently using a burn period to slow down fire spread at night, because the operational models tend to overpredict fire spread in the overnight hours. And one of the caveats of that is that we would actually underpredict fire spread in periods of real high wind or elevated dryness, where the fire doesn't shut down and basically enter kind of a creeping or smoldering state when there's much less wind. So we're looking at how to maybe do something a little bit finer there, maybe using dryness and some measure of fire spread potential to not put or reduce the fire spread by 90% or 100%, but maybe moderate it somewhat. But yeah, that's one of the limitations of the kind of the current approaches to modeling fire spread, is that the burn period approach prevents you from over predicting fire spread at night, but it may actually cause you to under predict spread at night in some, well, at least in cases where the fire remains active.
And then there's one related to the risk displayed, and basically related to fire size. And the question is really, is it average fire size that is displayed, or what exactly is being displayed?
Yeah, the way you can think of that is for each point that a fire is ignited, there's a size associated with that. And so you have at any point in time, you have a spatial distribution of modeled fire sizes associated back to a point. And an interpolation algorithm is used to smooth those out so that there's coverage in areas where, you know, a 30-meter pixel wasn't ignited. But yeah, it would be an average, you know, spatially averaged quantity within a neighborhood surrounding the, you know, the ignition area.
And then we get this question a lot. Basically, how do we choose which fires to run active spread forecasts on? And is there like a threshold of some sort?
No, there isn't really a threshold. The fires come in automatically from those two data feeds that I mentioned, and then can be added manually. And then we have a group of folks that are kind of monitoring those and removing fires. Sometimes we get what I call zingers, which would be a fire in the middle of the Pacific Ocean because somebody flipped latitude and longitude when entering it into the system. So there isn't any real formal threshold, but we try to get all big fires, at least all big fires that have potential to burn for a day. If there's a grass fire that gets to 1,000 acres and then it rains, putting it out, it has limited potential for, limited holdover potential, meaning it's not going to rekindle, or at least very unlikely to rekindle. So we might not have those. We try to err on the side of being over-inclusive. Often you'll see there's fires in the system that don't do much for days. So somebody mentioned this fire in San Mateo, which I think got to 20 acres. It's in the system now, but in all likelihood that fire is fully contained at this point. So it'll stay there for another couple of days until we take it out.
I think that's it. I don't know if there's anybody else that has any questions. Please feel free to unmute yourself and ask away.
Hi, Chris. First, I want to thank you for very interesting and detailed presentation. I just wrote it in the chat as well. And I wanted to ask about the accuracy of the forecast model. And do you do some hindsight assessment or some assessment of the accuracy of those fires? Yeah,
so everything that is run is saved and archived for later analysis. And one of the reasons for that is that forecasting the spread of a fire, in the future is a lot different than hindcasting the spread of a fire 6 months later. And so we want to archive and keep all the data so we can go back and do that analysis. But really the most challenging thing for doing that is that in a way you're comparing apples and oranges. We're comparing an unsuppressed model to the real fire that is suppressed. And so really that comparison is best done for wind-driven fires or fires early in their life before there's significant amounts of suppression on those fires. So qualitatively, the models work well for wind-driven unsuppressed fires. They don't work as well for heavily suppressed fires or for fires that are plume dominated or fuel dominated because of the lack of fire atmosphere coupling for those types of fires.
Thank you.
Great.
I've got one, if I can sneak a question in here.
Please.
By the way, the presentation was fantastic. The program is fantastic, and I'm so grateful to be included as part of this. The VIIRS and the MODIS data are fantastic for being able to show where the fire is now before we can get those not so often updated perimeters. But within the last year, A couple of organizations have started displaying Go 17 and Go 16 color-coded polygons, which is far more real time. That fire starts, and within 20 minutes, you can get a polygon on a map being read by Go 17. Is that something that you guys are considering incorporating into this?
The short answer is yes. So I showed some of the real-time RGB imagery. We have a fire product as well that is kind of the native product that's used to generate those maps. The challenges that we have is that the pixel size there is 2 kilometers. And so for small fires, it basically tells you there's a fire in this vicinity, but it doesn't really tell you that it's on the west side of the 101 or the east side of the 101, for example. But for large fires, it's actually quite useful. If you have something at the scale of like Dixie or Caldor, where it's, you know, tens of thousands, hundreds of thousands of acres potentially spanning 50, 60, 70 miles, that can be super, super useful. So it's I must sound like a broken record, but it's on the list. We have like a really long laundry list of things, and that one is probably gonna be rolled out within a few months here. I don't know that we'll be able to use that for initializing the fire perimeter. That's something we've talked about and thought about internally. It might be useful for saying, or for determining which sections or which segments of the fire perimeter are hot. My understanding is that those satellites can sense fires at about a 15-acre size, maybe 10 to 20 acres, but nominally 15 acres. And so if there's some part of the perimeter that's hot at that kind of length scale, we should be able to pick it up with those 2 kilometer products.
Great. I guess just to say that, we've recorded this meeting, and we'll be posting it to the project website, which is pyregence.org. There's a media page there. There's a link there, and I posted that here in the chat box. So I will just give you the heads up there. It looks like there's one more question here. What happens when your funding from CEC ends? So that is something we're working on. We're trying to find alternative ways of keeping the program running. And so, yeah, we're looking for partners and some other ways to generate revenue to support the program. So we're working with CEC on that as well. So.
Yeah, thanks, Shane.
Any other questions? Yes, otherwise we can let you go.
Okay, well, I just wanted to say, give a thanks to everybody for joining. Really appreciate you taking time out of your busy schedule to learn a little bit about what we're doing here with the PyreCast project, and also wanted to thank the California Energy Commission for funding this work. Thank you. Bye.
Everybody, thank you.
Thanks, folks.
Thank you.